We have Professor Vineet Sagula and Dr. Nanda, Satyasai Nanda with us. So this program is having more than 100 participants from different states of the country. Like a large number is from Rajasthan. Apart from that, people are from Kerala, Telangana, uh, and Andhra, West Bengal, Odisha, even Kashmir. Means approximately every state presence is there. And we are having most of the participants as faculty members, but many of them are UG candidates also. Willingly, they have attended it even though the exams are going on, but still they have joined it because they find that the course is relevant to them. So this course, I hope this will be very helpful for the faculty members, not only the faculty members, but for all the candidates, UG, PG, and PhD candidates. As far as the spectrum is concerned, we have the faculty and the researchers from electronics background, electrical background, and physics background as well. So this course basically is a superset of a course, Electronic Materials, Devices and Circuits, which is conducted by AICT in their minor course offered to electronics and communication engineers as VLSI Design in Technology. So this course is one of them. And we have added some more portions of that. The people who are doing the research, they can get benefited out of this. So this is a little bit about the course. Now I would request Professor Sahula to say a few words about this particular FDP. Hello.
Thank you, Menka. First of all, thanks to you for taking trouble to organize this program and interacting with all the speakers. Good morning to all of you, Dr. Nanda, Dr. Menka, my other colleagues from MNIT, all participants, faculty, students, and our speakers who are present here. Outright way, I should thank, it's my duty to thank on behalf of all of us to all the speakers and experts who have kindly consented for uh, devoting their time to actually make this journey of learning for participants quite exciting and interesting. I'm here just to let all of you know who are especially faculty members that UGC and AICTE have recommended that all the institutes should now start teaching in emerging areas. And to motivate the UG students in those institutes who are starting teaching the emerging areas, they have actually designed some minor comprising of 3 or 4 additional subjects in their UG, which every institute can imbibe. To enable faculty members of those institutes to offer these emerging areas, we have gathered a list of 5 to 6 programs in emerging areas. So I'll just like to tell each of you the way we have started our efforts, including this program itself, which we are now offering. So I have just small presentation just to help you understand quickly what are the provisions of UGC and AICT and what academies are doing, including MNIT Jaipur. I hope my slides are visible to all of you.
Yes, the slides are visible.
So this is what academies are trying to enable and make faculty members, our faculty colleagues all over India in different institutes to start teaching in emerging areas. And we have a help from AICT and UGC through their recommendations. So if I look at this, AICT UGC have approved the minors for UG. So apart from their total credits, for UG degree eligibility, they can take 5 more courses, maybe 3 credit each, and go for minor. Those minors have to be floated by respective universities and colleges. And we understand that major difficulty is in teaching those emerging areas topics, and hence we are offering the FDPs in those areas now. FDPs covering those areas which are defined in minors by AICTE and UGC. So just have a look at that. You can see the letter from Professor Sitaraman Sahab, where he describes how these minors have to be floated, and each college and university is now free to offer those minors so that they can attract good students who are interested in the emerging areas specialization. Model curriculum for minors also is available on the AICTE site. These slides will be shared by you by organizing team, Dr. Menka and other Ramesh and Geeta. And we have taken up that mission to actually offer our FDPs aligned with those minor areas, right? This is the letter from Professor Sitaraman Sahab, which says that all of the engineering branches, right, they can offer elective courses in emerging areas. And they have defined that emerging areas: artificial intelligence, IoT, blockchain, robotics, quantum, cybersecurity, 3D printing, AR, VR, VLSI design, and so on and so forth, right? There they say that the UG students can take some extra subjects, which are 3 to 5, and then go ahead. What he describes actually for faculty is this. AICTE highlights that there is a shortage of faculty in emerging areas. True. But he also says that the faculty from core area may be allowed to teach, right, the emerging area subjects after they complete at least 10 courses, online courses from MOOC, SWAM, NPTEL, and GOI portal. So our AICTE Academy is a GOI portal and GOI governed funding, and we have a funding from Ministry of Electronics. So our courses are eligible there. So any faculty who chooses to go through 10 credits, which is about 3 to 4 FDPs, which we are offering, they are eligible to teach the emerging areas topics, provided their institute offers minor in that. So any one of the things have to happen first. So we have taken up this mission to bring FDPs in those lines. So these are the minor streams by the for the UG recommended by the AICTE. The current program, which is starting today, thanks to Dr. Menka Yadav, is one of the program in this scheme, VLSI design. We are also offering joint program for blockchain and joint program very heftily attended by more than 1,000 candidates. We are into third program currently, QT03, QT01 and 02 are over, and we'll go up to QT06 in future. VLSI design, we are offering the first course and we'll go to the 6 courses in the due course of time. We are also starting programs FDP aligned to those subjects defined by AICTE document for minor syllabus and that part. These quantum subjects defined in the AICTE document, and this is what we are offering. 3 of them already in pipeline, already over, and rest of them are to be offered in the future. If you have missed any of these, we'll offer them in a self-paced kind of a thing. You can still go through that. For AI machine learning, we have just starting one of the program today itself, and we'll offer some of them in due course of time. This is starting maybe today or yesterday it has started. So even if you have missed it, or some of your colleagues you can convey, even if they have missed one day, we'll try to adjust and bring them up to the onboard for the rest of the 19 days or 9 days that way. Blockchain, we are offering blockchain starting from the 13th May. For VLSI, this is one of the program which we are offering, and we'll offer other courses in due course of time till September. So please look forward to other programs. And what we offer is, in the end, we'll give you a PG certificate saying that you have specialized in FDPs and you have attended 3 to 5 FDPs in that area. this will be a separate certificate than your individual FDP certificate. And this is actually an endorsement that you have specialized in one of the areas, having that part. What UGC says is they have come up with some scheme on Bharat 6G document under the vision of our Honorable Prime Minister Modi ji. And they have formed a technology innovation group and come up with a 6G vision document. We already have 6G, 5G, 6G lab in our EC department. The coordinator himself is present here. He can even enlighten us about what activities he is taking up under that lab. Dr. Ajay Nanda, I will request him for next to me. What they say is they have a team hosted by Department of Telecom, and they have recommended some potential research topic for PhD program and some of them for PG programs, right? The basic stress for them is for PG is terahertz communication, optical and satellite communication, right? This terahertz communication also includes wireless, 5G and 6G. And for UG, we also have some listing given there. So what we are offering courses are also under 6G wireless, various courses. And for terahertz also, we are offering many courses. These are name of the specialization under which we'll give you PG certificate if you complete 3 to 5 FDPs in those areas, right? So this is very much in pipeline just coming up, which is antennas. I think next month we are going to offer it. This is already covered. Rest of them we are also going to offer, and you can look forward to specialize in different areas following our part. This is the offer if you attend 3 to 5 FDPs, right? Covering about 15 to 18 credits.
Hello. Hello.
So I'm sorry, I lost my internet connection. I'm not sure where I lost it.
Sir, you are audible now. You are audible now, sir.
I think I am almost over. I think 2 slides are remaining, so I can just cover that up.
Okay,
I was
sir.
discussing about UGC minors, and will actually award the PG certificate diploma if you complete 4 to 5 FDPs. This will be a separate certificate over the FDP certificate that way. Fine. So I wish you all the best and good learning. Thanks to speakers and to you gathering here. Thanks to Dr. Menka for taking efforts to organize such a program. Yeah. Thank you very much.
Thank you so much, sir. Now I invite Dr. Nanda to say a few words about this program of and EICT Academy MNIT Jaipur. Dr. Nanda.
Yeah. So I welcome all the participants to this very important FDP on semiconductor devices and sensor application and research perspective. As all of you know that in last within 5 years or very precisely within last 3 years, the government has given a lot of focus on the semiconductor industry and uh, academia also to produce manpower for the semiconductor industries which are the forefront for the development of India's semiconductor mission. So this is a course which is very relevant in terms of that to towards building manpower for the uh, uh, semiconductor industries. So this course will focus on the semiconductor devices and sensors, and I can see a lot of experts from various IITs and NITs are also from CSIR labs are going to deliver the talks in the next 2 weeks time. So our EICT Academy, as Professor Binit Savla sir has told, that a similar kind of courses, bunches of courses we are going to offer to so that every participants can, whoever is attending 4 to 5 courses on a allied area can get a PG certification in that particular area. So like the semiconductor industries, 5G and 6G communications are also on the highlight, and a lot of research work is going on on the wireless communication as well as the terahertz technology, building antennas and signal processing for that one. At MNIT Jaipur, we have received one of the such laboratory out of the 100 labs that have been established all across the country. And we are going to offer similar kind of programs as Sir has highlighted in the next month. And presently, the Department of Telecom is taking all the initiative for such kind of program which are on the advanced cutting edge of research, and our motivation is to train the next generation engineers about these upcoming technologies. So I again with this expect a fruitful learning for all the participants who have joined in this particular FDP for semiconductor devices and sensor. Thank you all.
Thank you so much, Dr. Nanda, for the enlightening words about EICT Academy, MNIT Jaipur, 6G programs, and VLSI related FDPs going on in MNIT Jaipur, and of course, enlightening about the PG certification programs, which is approved by AICT and UGC. So I hope our participants would be learning all these things and they will be applying to their own skills. The students will be applying to skill up themselves, and the faculty would be applying to nurture the upcoming future generation of the engineers of the country. So we wish happy learning to all of you. And with these words, I would actually complete the inauguration session, and we will be starting the first lecture after 5 minutes. After 5 minutes, we will be starting our first lecture of this FTB. So thank you so much, and let us come back at 11.
and start the thing
So within 5 minutes, we are going to start it. So
on this link itself.
Do not run away. Keep the link joined, and you can take water or something by that time. And let's start at 11:50. Thank you so much. Yeah. So. Yeah. Good morning, everyone. Welcome to Semiconductor Devices, Circuits and Sensors Applications and Research Perspective FDP. So let us start the program now. This is the first lecture of the day. We will be discussing in this lecture types of materials and on the basis of that, what are the different types of semiconductors. I hope it is audible by all of you. Please share whether it is audible or not. You can share in chat whether it is audible, so I can start it. Okay, thank you so much. I don't know whether it is recent chat or okay, fine. So basically, let us start with the outline of this particular 1 hour. First of all, we'll focus on why this subject is important. Uh, Already the importance of multiple subjects from the ministry point of view, countrywide skill nurture and all these things, it has been discussed by Professor Saula and Dr. Nanda. Now let us discuss the market perspective. So in order to discuss that, let me take a simple real-time applications of VLSI. Let me take. So there are different real-time applications, like we have phone, TV, laptops, and headphones. It might be wristwatch, smartwatch, health band, etc., etc. We have in defense, aviation control, onboard control, satellites, aircraft, spacecrafts, etc. And then we have a special purpose like ADCs, analog to digital converters, digital to analog converters, GPUs, TPUs, etc. So these are the different applications which we can see in our surroundings, in our day-to-day life, right? So these applications are costing us more, and these applications are contributing the real market size of VLSI industry. So this is the projected worldwide industry, which is shown over here in this diagram at the bottom. You can see this is the diagram. In this it is shown. So in this you can see that in 2033, this is expected to reach $1.4 trillion. Currently, it is approximately $0.8 trillion. It is approximately worldwide economy. If we take into consideration the Indian market perspective, there is a foundation named Indian Brand Equity Foundation. This report, which was shared, the CAGR data in 2015-2020, there was 29.4% growth before this in from 2015 to 2020, and nowadays it's been exponentially increasing since last 5 years. In Corona, we might have seen exponential boost in the laptops and smartphones market. There are major players in the market like multinational players: Intel, Nvidia, Qualcomm, Broadcom, Samsung, Texas Instruments, AMD, ARM, IBM, Analog Devices, ST Micro, Electronics, MediaTek, Microchip, Xilinx, Cadence, Amazon Synopsys, etc., etc. There are many more to be listed, but these are the major players. These major players are offering handsome amount of salary. What are the pay and perks offered to the VLSI engineers? This is given over here. Average package is approximately 8 lakhs per annum in India, and maximum package is offered by NVIDIA is 48 lakhs INR per annum, especially to NIT and IIT people. And if you are having the experience, your growth will be exponential. It doesn't really make the college brand. It matters what the experience is. There are 3 types of jobs in the market: front end design, back end design, and fabrication.
Front-end design includes like RTL coding, which is based on Verilog, VHDL, system Verilog, verification, etc., etc. Testing is also one of the part in the same. And then there is backend design, designing using Cadence, layout design, and placement, routing, floor planning. All these things are the backend design. Then there is one part is fabrication. So fabrication is the actual hardware is coming into the picture. So this fabrication actually is a little bit different. The people who are working in the fab labs are specifically for that fab lab only, because it is a very tedious process and special engineers are required for the fabrication laboratories. Now, before proceeding to the types of materials for electronics, let me discuss the market perspective, the Indian market perspective. So this we will discuss with the help of some calculation. So all of you are having mobile phones and laptops. I presume everybody on average is having the mobile phone, which is costing you 10,000. A smartphone everybody is having. Maybe some of you are having more, or maybe some of you are having less. So let's say 10,000 is the value of your mobile phone. Okay. Now you are having the laptop also. So the laptop, let's say the laptop, the average value of the laptop is what we are going to do.
Yes. Yes, I'm sorry. There was some internet related issue was there. So let us back to the talk. So laptops are costing, let's say, around 50,000. Now, what is the age of mobile phones? You may type in the chat box. Let's make it interactive. You may type in the chat box. Do it makes some sense that every mobile phone, average age you can have 3 years or 4 years? Do you agree? If yes, say yes, or you may just type Y in the chat box. If you agree with this, you may just type Y in the chat box, and then I would be able to. Yeah. So average age of the mobile phone is 3 to 4 years. So let us take it 3 years. Or if you want to take it upper side, let us take it 4 years. So it is 4 years. But laptop, let us take the average age is 6 years. After 6 years, it is not working well. Either the technology has been actually upgraded, or maybe the system is not working because of a number of problems seen in the system. Battery is not working, the screen is not working, touchpad is not working, and similar things can be there. Okay. Am I audible? Am I audible? Yes, ma'am. Yes, yes. Okay, thank you so much. Yeah. So let us take 6 years is for the laptop. So it means contribution from every mobile user. Indian perspective will calculate. And if I am taking, let's say, instead of 6 years, let us take it 5 years. Let me take laptop, average age is 5 years, so that it can be easier to calculate for us. So the average age for the laptop, average price becomes 50,000 divided by 5, this becomes 10K. We are 140 crores. If I presume that 50% of the population is having the smartphones, okay, instead of 50%, let us take 50 crores of us are having smartphones. And out of those 50 crores, 20 crores are in this particular category who are having the smartphones and going to change every 4 years. Smartphones, they are going to change every 4 years. So what it will lead? These 2.5K into 20 crores. So these 20 crores are changing mobile phones every 4 years. So it means 2.5K rupees, 20 crores. This is the mobile market per annum. To make it a little bit easier, let me take it 24 crores are having this particular scenario. So if I want to take it per month, it is going to give me 5K crore per month revenue only from the mobile phones. 5K crores. So 5K crores means it is 500. Is it correct? Billion? 500 billion is the market. Billion rupees is the market. Approximately, you can say 5 to 6 billion dollar is the just mobile market per month. So if this big size of the market per month we are having in India, this is just the mobile phone market I have calculated for you. Just like that, if you are going to calculate this laptop, desktop related market, you will find similar or a little bit higher. There are other things like smartwatches are there and other things are also there. If you calculate for that, you will look into it that we have $1 billion per month market in India. So this market, it means we are actually having a very good market. It means if we are nurturing our students, our faculty members in this area, we can actually create the job seekers and maybe job providers also in the same segment, and multiple people will get benefited because we are the consumers right now, right? We are the consumers. And if we are preparing the manforce, it means there are chances that it is giving multiple benefits in terms of the job providing, in terms of indigenous manufacturing and other things related to it. So is it clear to all of you? Shall we proceed to the topic now? Any question related to this, you may please proceed to ask. You may type in the chat box if so far you have any question related to this. Do you agree whatever calculations I have done and I came to the figure 500 billion rupees, or let's say approximately $5 billion. Or dollar is actually 87 rupees cost approximately. But let me take 100 rupees equal to $1 for the simple calculation. So it becomes $5 billion revenue just from the mobile phones. And this is in our country, in India. This is in India, right? So it means there is a lot more to do in our country related to the manufacturing of the semiconductor industries are projected to be there in India in upcoming 4 to 5 years. There is chip to startup program across the country. We have multiple labs which are costing crores of rupees. Those licenses we have. So the thing is, users need to nurture your skills so that you can be employable in that particular field, right? So now let us, with this note, let us start with the main topic. So this course is the very basic course. We are going to start with the materials, what types of materials are there, and which type of materials we will be using in this particular course. So basically, we are targeting electronic solid state devices. What is the meaning of solid state? Solid state means the electrons are flowing in the solid. The state of the material is solid. We are having the flow of the electrons in the solid state only. So we call these devices or these type of electronics as solid state electronics. What was the previous to this? Before this, we used to have vacuum tubes. If you remember, vacuum tubes were not the solid state devices. There was one cathode was there and one anode was there. So there was very high electric field was applied, and this very high electric field, this space was vacuum. This particular space was vacuum, and this very high electric field was actually having the electrons which were actually starting from here to from source to target. Electrons were going from one part of this to the other part, cathode to anode. Then the current flow was seen. So this was the vacuum tube related things, right? So these were very bulky. Apart from that, these were not. These were actually very power hungry circuits, not only bulky but power hungry circuits. So these are not going to work in today's scenario. So if it is not going to work in today's scenario, we have the replacement, that is solid state electronics. This solid state electronics is going to give us the benefit, whatever we had. This solid state electronics is having the benefit, whatever we had, with the low power, high efficiency, lightweight. One is low power, then high efficiency, high performance, we can say, and lightweight. Along with that, lightweight, that is really much more needed. Why lightweight will work? Because if we are thinking about the aerospace and related things, for example, Chandrayaan, right now it was before a few days, Chandrayaan was landed successfully on south pole of the moon. So there was payload. That payload was expected to deliver lot many studies from the moon surface, and lot many things were there which were actually making it successful, the landing successful. That electronics, if we would not having the low power, high performance and lightweight electronics, then the payload would have been increased, and that payload actually will be costing threefold while sending that payload into the any of the planet or maybe moon or somewhere else. So that is costing us very much. Likewise, there are multiple things. For example, we are having phones. These phones are basically low power devices. Phones are low power devices. If these are power hungry devices, in that case, it will be like if we think like vacuum tube related devices are being replaced. In that case, these would have been very bulky, and it would have been very difficult to carry the mobile phones along with us, and the performance was also not really good. So if the performance is not really good, we could not able to do whatever the things we are going to do with the help of mobile phones nowadays. So this is the basic thing related to why we are moving towards electronics and related things. Now let us proceed to the types of materials. So types of materials. Basically, types of materials will depend on the uses. For example, if you are using the type of material in mechanical. So in the mechanical, you will be talking about the fatigue, fracture, how the strength is there, tensile strength, maybe yield strength, elongation. All these things are required in civil. Civil means it is related to the infrastructure, maybe insulation, how it is working with the environment, whether it is working well, load bearing capability and all. We will be going with those type of materials. For example, steel is one of them. Iron is another. Pack labs. In pack labs, we used to have like having different kinds of these medical things we have to check. So for that, we have liquid and related things. Those type of materials are required. For surgery and related things, for example, some artificial arm or artificial some bone is being replaced. So it means that has to be compatible to our body. This has to be compatible to the strength has to be good enough. Whatever strength our bonds were going to give us, and all these things we have to take into consideration. Other might be food technology, so we have to think about that it is not expected to be homogeneous. It has to be uh, good and give us a strength. So all these things we will be talking about. So in this course, we are only concentrating on the materials related to electronics. So basically, if we are talking about the materials which are related to electronics, we will look into the electrical properties. And what are the electrical properties? So these are the electrical properties: resistance and conductance. What is resistance? Resistance is actually how much you can resist the flow of the current is the resistance. Flow of the current means flow of the current is what? dq by dt. Current you can represent by dq by dt means the rate of flow of charge per unit time is the current. So this current flow of charge dq by dt. This is the current means these many charges per unit of time are flowing. Resistance will oppose these charges to flow. And that's what resistance. Conductance is the virtue of the material again, and this is just inversely proportional to the resistance. Conductivity is how much the material is going to support the flow of electrons or flow of the charge carriers. That is the conductance. So based on the resistance and conductance, there are three categories of the materials. Electronic materials are categorized in three parts. First one is the conductor. Second one is the semiconductor. And third one is the insulator. So three types of materials are there: conductors, semiconductors, and insulator. What are the conductors? Which is having very good conducting capability. Semiconductors, which is having moderate conductivity, and insulators are not having any conductivity. Or negligibly small conductivity is there for the next category. Yes. So before going into the details about these three types of conductors, let us have these few definitions. First one is the conductivity, then resistivity. Conductivity is the ability to conduct or to carry the current. Any material, how much it can be able to carry the current, that is the conductivity. How the conductivity is being defined? So conductivity of the material is defined as mobility into the charge. So that charge is given by, for example, let's say it is N type of semiconductor is there. You can represent by NQ, that's the total charge, because and then mu is the mobility. So this is the conductivity. If it is P type of material, you can put it like PQ into mu P. So that is the conductivity. Resistivity is nothing but 1 upon conductivity. Resistivity is defined as 1 upon conductivity. Resistivity is a virtue. So in order to find out the resistance, how the resistance will be found out, resistance can be represented as given in the formula. Resistivity into the length of the wire divided by the cross-sectional area. This particular is given for the wire, but this is applicable for all types of materials. Like for semiconductors, also the formula will remain same. It will be decided how much is the length of the semiconductor divided by how much is the cross-sectional area of that particular semiconductor. So that will be the resistance offered by that particular semiconductor bar, or let's say the conducting bar or something else. Now, next definition is the band gap. Band gap is defined as EC minus EV, and it is represented by EG. E is for energy, G is gap, energy gap. Conduction energy band is defined as EC. Valence band is defined as EV. We will come to this. And then there is vacuum energy level, which is actually the free space energy level. And there is one thing called as Fermi level that is applicable to all the materials. So Fermi level is the level where 50% of the probability of finding electrons or holes is going to exist. We call that as Fermi level, right? What is valence band? Valence band is the band of energy band where we can find all the electrons are in pair. All the electrons are actually having the bonds, strong bonds. Conduction band, we have the free electrons. Electrons are free to move. Those are the conduction band. And then we have Fermi level, which is having the probability finding electrons 50%. Electrons and holes are complementary to each other. So we can say finding the electrons 50% means finding the holes also 50%. That is our Fermi level. Okay. Now, before going into the categorization of different types of materials, let me introduce you from discrete energy levels to the band theory, how we are going to reach. So see, first of all, we have some atom. Let's say this is one atom. This atom is having its own energy levels. These energy levels will be founded in discrete levels. One level, let's say E1, then E2, E3, E4, E5, like that. For example, for hydrogen, you might have seen the levels, energy levels are clearly different levels. Okay. Now these are discrete levels will get converted into the energy bands. How these will be converted, that is shown with the help of this particular diagram. In this particular diagram, you may see what is shown over here. There are different levels. First one is this. These are the occupied levels, completely occupied levels. Then there is the outermost cell. In that outermost cell, these are actually the valence band and the conduction band levels. So these valence band and conduction band labels are there for the atomic structure. Atomic structure is having a distinct level of the valence band, conduction band, and completely filled cells. So these, if you are talking about a simple atomic particle, you are talking about, these are different regions. Now look at the x-axis, the interatomic separation is going to decrease in this way. If you are moving left hand side, the interatomic distance between the atoms is decreasing. If this interatomic distance is decreasing, what is going to happen? The outermost electrons will come closer. They will try to form, if you talk about semiconductors, they will try to form covalent bonds. Covalent bonds is a theory which is having like sharing of the electrons. Means the electron will be counted in this particular atom also and that particular atom also. So it means their energy is also being restructured. How it is restructured, that is decided by this diagram. So as soon as they are going to come closer and much more closer, these discrete levels are getting converted into bands. These are the bands. And this is the particular distance which is known as the equilibrium interatomic distance, interatomic spacing. At this particular distance, our most widely used semiconductor silicon will be having some 5 angstrom distance, approximately 5 angstrom distance it will be having. And there will be these energy levels. The bottom energy level maximum from here to here, this is the valence band. And from here onwards, it is known as the conduction band, which actually has been created from all the conduction level, means the higher level electrons that has been created. So this is the theory behind, right? So we proceed. Understood? Yes. Am I audible? You may type Y in the chat box, or if some question is there, you may type the question also. Okay. So now let's figure out what is the category of different types of materials. So there are different, remember we are only talking about electronic materials in this particular subject because this subject is related to electronics and applications. There also we will only talk about semiconductor and related things, right? So insulators and conductors are also the part of your electronic materials. Like conductors will be used for the contacts. Insulators will be used for the insulation purpose. For example, you are preparing, let's say MOSFET. So you need one insulator in between the active channel and the gate contact. You need insulating material. So that's what, for the completeness, we have discussed all three materials all together and their properties. So first of all, there is electrical conductivity, on the basis of which we will be segregating the three types of material. For conductors, the electrical conductivity, which is the virtue, which is going to decide how much current can flow. So the conductivity is going to be very, very. And then, so if you can recall the conductivity Ohm's law for the semiconductors, or even in journal, you can have J is equal to sigma E. J is the current density, ampere per meter square. Sigma E is the conductivity of that particular material, and E is the electric field, dB by dx. So J is equal to sigma is nothing but the another form of Ohm's law. If sigma is going to be very high, J is what? I by A, current per unit area. It means the current is going to increase. So sigma is more, the current is going to increase. That's what we are looking for. Semiconductors, this is expected to be conductivity, it's expected to be moderate, but it actually varies with the temperature. Why it varies with the temperature? The reason being, semiconductors, the how many free electrons are there, those will keep on varying with respect to temperature. Next one is the insulators. So the insulators are having very low conductivity, negligibly small conductivity level is there for the insulators. So you can say that the conductivity of insulators is 0, but at times it is not exactly 0, and that very small amount even actually contributes to some leakage and some issues in the devices. So we only term it very low. As a layman, you can make it 0, right? But being an engineer, faculty member, researcher, you have to notice that this is very low, not 0. Another thing is energy band gap. So energy band gap, whatever we have discussed, the energy band gap is the band gap which we have discussed already. Just a minute. Yeah, I'm sorry. So energy band gap means the band gap between the valence band and the conduction band. Valence band is the fully occupied, which electrons are completely pure, no restriction. Conduction band electrons are free to move here and there and contributing to the current, especially in conductors. So basically the energy band gap is expected to be overlapping in conductors. This is going to overlap, means there are free electrons in a good amount in the conductors, in the conduction band. So they are free to move here and there, and as soon as a small electric field, very small electric field is seen, these will be actually from random motion, these will be aligned into a particular direction depending on the electric field direction. And that's what the current flow starts. Next one is the semiconductor. So the energy band gap for the semiconductors is small. It is not very small, but small enough that we can modulate this particular band gap. We can tune it and we can make the devices on or off. On or off means we can make the semiconductor to conduct or not conduct. We can control it depending on using this band gap. So this typical value of this is starting from few electron volts to 2 to 3 electron volt. It is the typical value, although I have listed something else in this PPT. because most of the semiconductors we are using are lying in this range. That range I have reported on. Insulators are having the large energy band gap, very large energy band gap. So the electron from conduction band is not able to come to the valence band and vice versa. An electron cannot go from valence band to the conduction band. That is also equally true because the energy level is very high, 5 electron volts and more. That is very high energy level. Few of the examples of all three categories I have listed over here. For example, conductors are copper, silver, aluminium. Likewise, semiconductors are silicon, germanium, gallium arsenide, and all these. Insulators are like glass, rubber, wood, silicon dioxide, HF42, and other related to this. What is the temperature effect on these materials? So basically for the conductors, we already have ample number of electrons. So the resistance will keep on increasing with the temperature. Why? Because already there were ample number of electrons. If you are increasing the temperature, it means the energy, increasing temperature means you are giving more energy to the electrons. More energy to the electrons means they will have more energy, but already that space was congested. So if it is the case, it means these electrons are going to disturb to each other. So instead of supporting to the current flow, these are opposing the current flow somehow. So increase in the temperature will increase the resistance and hence decrease the conductivity of the material, conducting materials, conductors. Next one is the semiconductor. So the conductivity of the semiconductors will keep on increasing up to some temperature for the semiconductors, and after that it decreases. So the curve will come somewhat like this, and then it is going down. For semiconductors, it will go in this. And for conductors, it is decreasing. And for insulators, almost there is no change for insulators. There is no change in the resistance or the conductivity. So what about valence electrons? Let us discuss about valence electrons. That is segregating whether it is a conductor, semiconductor, or insulator. So valence electrons will be 1, 2, 3 in conductors. For semiconductors, it is exactly 4. We can see the group 14 or the group 4 elements. Previously it was group 4, nowadays it is group 14, it is called in the periodic table. Those are having the elements starting from carbon, silicon, germanium. This is the line we have in the periodic table. So carbon, silicon, germanium, strontium, Pb, all these are the category in group 4 elements. But most widely will be using elemental semiconductors, these two, which is silicon and germanium. These are known as elemental semiconductors. Carbon is generally not used as a semiconductor device in the electronics and related things because it is having a little bit higher band gap as compared to silicon and germanium, and mobility is a little bit lower. So it is not going to give us good enough current. But yes, there are many electronic applications like thin film screens, foldable screens are there in which carbon and related things are used as a semiconductor material. And most widely we'll be using silicon germanium, or maybe the compound semiconductors will be using. We'll come to that, what are the compound semiconductors and all. So yeah, insulators will be having basically 8 electrons mostly will be having in the outermost shell. Then what are the applications? So basically applications are conductors will be used in the wiring, connections, power transmission, and all these things. These are also used for shielding purpose, insulation, or like you can say the chambers. Shielding means stopping the other type of electromagnetic waves coming and entering into your space. So dome-shaped rooms can be prepared, which are prepared completely with the help of conductors. They will be taking to stop all the electromagnetic waves which are coming, and all the equipments inside that particular shield will be actually free from any kind of radiations, willing or unintended hazards, radiation related things. And especially in defense applications, you can have that thing. If there is some very sensitive information is there, that particular room must be shielded completely. So for shielding purpose also, these conductors are used. And next one is the diode, transistors, solar cells. We will be using semiconductors, conductors. We'll be using in diode, transistors, solar cells, semiconductors can be used. Then the third category is the insulators. So insulating layers, casing, support materials, sometimes we'll be using the insulating material. Now, based on the band gap, I have given the total view of all the three elements over here. So this first one is the condenser. You can see the valence band and the conduction band. These are overlapping to each other. So it means the electrons are always ready to conduct. We need not to make much more electric field use in order to make the electrons flow. Next one is the semiconductor category. In the semiconductor, you can see there is a gap between the valence band and the conduction band levels. And this band gap is having somewhere in the mid, that is known as the Fermi level. This one is the Fermi level. And this Fermi level is having the probability that 50% of the electrons, 50% of the holes can be actually here. That's the probability of the electrons and holes finding. So why it is shown that Fermi level is here, why we are saying that this is the forbidden gap. So forbidden gap means no electron can exist or hole can exist over here. So basically this is average out that this is the minima of the conduction band, this is maxima of the valence band. And both of these are averaged out in order to figure out that where the 50% can be on the electrons or holes. So based on that, there is a numerical value, and that is what the Fermi level. For insulators, you can see that there is a very large band gap between two, and this very large band gap is responsible not to flow any transition from valence band to conduction band and vice versa. So if no transition of the electrons is possible, it means these are not able to conduct the current. That's the thing. So in this left-hand side diagram, metal, semiconductors, and insulators, the different categories with examples and their conductivity are listed over here. You can see for conductors, like we have copper, aluminum, iron, steel, wire, etc. The conductivity is approximately 10⁸ per ohm per meter. While for semiconductor, it is 10⁻0 per ohm per meter. Lead sulfide, germanium, silicon, etc., etc. So lead sulfide is actually the compound category of the semiconductor. There are two types of semiconductors based on how these are prepared. So one category is the elemental semiconductor. Elemental means the element, pure element is taken from the group 14 of the periodic table. So those are the elemental semiconductors. For example, germanium, silicon, these are the elemental semiconductors. Another category is the compound semiconductor. Compound semiconductor means two or more elements from the periodic table are taken in order to prepare a semiconductor. So generally, people used to take group 13 and group 15 elements all together in the equal quantity, or maybe group 12 to group 16 elements. They have to take in equal quantity or a mix and match of those particulars, so that we can, on an average, every element can have 4 electrons in the outermost cell, and sharing can happen. That's the thing. So based on how materials you are going to choose, which are the compound materials, the band gap actually is modulated. That modulated band gap actually offers you the application specific things. For example, solar cell is having a little bit different band gap. Laser light is having a little bit different band gap. If you are having an LED, which is going to give you green color, red color, yellow color. So it means that there is something different wavelength, which is decided by the energy levels, Eg, band gap between two. So energy is h nu. H is the Planck's constant, nu is the frequency. So h nu is the energy, and this energy actually is the photon coming from here to here. It is going to release the energy, or going from conduction band to the valence band to the conduction band, and vice versa, whether it is consuming that energy or releasing that energy. So that is going to decide the applications and the band gap. What application we should have, depending on that, we will be having the material. We will be preparing the material for that particular application, achieving that particular band gap, right? So single element versus crystal, how it will look like. Let us have a look at this. So the first one we have taken for a conductor. So in this particular case, copper atom is taken, and copper atom is having 29 electrons. So you can see over here, one electron is there in the outermost shell. This one electron, instead of attracting many more electrons in order to make the outermost shell stable, we need to have 8 electrons, right? So this one electron attracting 7 more electrons, it seems to be very difficult task, right? So it is easy for this to give up this electron and come to the stable state, right? So because of that, this is actually conductor, because it is going to give up that electron. After giving up that electron comes to the vacuum. Okay, it is freely available to the outermost shell of this, and here it can move here and there. So this electron is responsible for the current conduction. Next one is the semiconductor. In semiconductor, you can see this is the example of silicon. Silicon is having the atomic number 40. So this is the electronic vinyas of this. So 2 electrons are there. After that, 8 electrons are there. 2 plus 8, 10, and in the outermost shell, there are 4 electrons. So these 4 electrons, in order to make this particular atom into the stable condition, we need 4 more electrons. Those 4 more electrons, how we can have? So those 4 more electrons, these 4 are neither can be given to someone, nor 4 can be taken from some other atom. So there is a concept of covalent bond which comes into the picture for the semiconductors. So this was the elemental atom. When we are having multiple such elemental atoms, these are coming closer, and much more closer. So there will be a particular space where the equilibrium is achieved. Means two atoms are sitting in this position. Let's say one can sit over here, another can sit over here. These cannot go far away from this. So this comes to the equilibrium, right? So this equilibrium actually is represented in the next diagram. And over here, you can see, for example, this central atom you can look into. So this is sharing two of its electrons. One of the electron of this is shared, and other of from the other it is shared. Likewise, one of this and another one from the other. So 4 electrons of this central atom and 4 more electrons are taken from the neighboring atom. So one electron from each. So you can see this is having four electrons of its own, which are shared by the 4 neighbors by taking one electron of each. So in this way, it is having its outermost shell 8 electrons. And likewise, the neighboring atoms will also have 8 electrons. By the similar sharing fashion, those will also have 8 electrons in this type of cubic structure. So this is how the silicon atoms will come closer. They will make the covalent bonds. And because of this covalent bond, the energy is being redistributed. How this is redistributed? Let us see over here. So it is redistributed in this way. So it is shown that how it has been redistributed. Yeah. So this is the diagram here. This was the category where single atom was there. Then you are creating multiple atoms to sit together. So you are achieving this category. And this is the space where the equilibrium is achieved. What is the meaning of this equilibrium? Means you cannot, two atoms cannot come much more closer than this. So there is the intra-atomic distance, which is fixed or Stephen, that decides that at room temperature 1.12 electron volt is the band gap between conduction band and the valence band of the silicon atom. So silicon material, not atom, material. So our focus will remain on silicon mostly, unless until it is not specifically told. So 1.12 electron volt band gap at room temperature for silicon is the standard one. For germanium, it is lesser. And based on that, the properties are getting changed. The conductivity and resistivity, all these things are changed for different materials. Yeah. So semiconductors based on photon transistor. Next is the semiconductors based on photon transition. So the photon is coming from the conduction band to the valence band. This is EV. This is your EC. So this EC, we are showing it with a straight line. But actually, this is not a straight line. This straight line we are drawing in our semiconductor bar. This is, let's say, our semiconductor bar. So in this particular, we are drawing the straight line that this is the minimum of the conduction band for all the atoms available in that particular semiconductor bar. That's how this we are showing this with a straight line. But on EK diagrams, if you will have a look at, so you will see that this is the K number and this is the energy. So there is a parabolic relation between the EK diagram. So the minima of the conduction band of this and maxima of the valence band, if these are having the same vertical axis, then we will call this as direct energy band gap materials. Okay, direct energy band gap materials. It means the electron coming from here will jump here all together and it will release in energy E equal to h nu. So you can see over here, this is easy band gap, right? So band gap means it is going to release that energy. So if that energy released is in the visible spectra, whatever energy is released, we'll be able to see that particular light in that particular color, right? If it is not there in the visible spectra, then it is not visible to us. So all the LEDs are working on this principle and photodiodes are also working on the similar principle. Photodiodes will take the energy, LED will release the energy. But at the same time, if we talk about the indirect semiconductors, so here there will be one trap position or the defect position. With the help of that, the particle from here will reach to the valence band. So there is no directly coming the photon from the conduction band to the valence band. This is the trap level. This is the defect level. So it has to come to the valence band through this defect, right? So that's the difference between the indirect and the direct band gap semiconductors. So silicon basically is the indirect band gap semiconductor. So what is the EK diagram? EK diagram you can see over here. This equation E is equal to h cut square K square upon 2m or h square. H is the Planck's constant. H cut is the reduced Planck's constant. H cut is denoted by this. That is h upon 2 pi, right? So E is equal to h square K square upon 8 pi square m. This is the formula. We are getting this formula from the Schrodinger wave equation, which is the standard equation for the waves, electromagnetic waves and all these type of waves. And here this K decides the Brillouin zone. So you can see the diagram which is available on the right hand side. K is the wave number which is going to decide the Brillouin zone, which Brillouin zone is available. So the EK diagrams from this relation, you can see that this is parabolic diagram. So next one is the silicon crystal structure. Silicon crystal structure is actually, this is a diamond cubic structure. And it is shown over here in this, it has been shown. You can see diamond means one is there in the one element is there in the center. And then 4 elements are there. And those are not in the one plane. They are all 5, all atoms are not in the same plane. There's a particular angle for each and every atom to get connected to the central atom. So this is the structure, unit cell of the silicon crystal is shown over here. So each silicon atom has the 4 nearest neighbors and how it is connected, that there is a particular angle of connecting line between 2. And this is what it is created. So maybe if it is working, let me show you. So you can see this is the diamond cubic structure. These elements are not in the same plane. Diamond cubic structure means you can see that there is a cuboid kind of a structure. This cuboid kind of a structure, what is the use of it? Will come to this. So you can see this is a cuboid kind of structure. And if we call that there is a crystal, so crystal means what? Yeah, crystal means repeating the similar kind of pattern is being repeated when the material is prepared. For example, we are having sugar or salt. These are having the crystal structure. Means a regular pattern which is being repeated to prepare a bigger amount of that particular material. So silicon is a crystalline structure, and this is diamond shape of the structure, which is recently shown to you. That type of structure is seen. There are other structures available for different materials. Like this is the primitive cube. The first one is the primitive cube. Next one is ant center. Third one is the body center. Then the face center, and then again the 2 monoclinic lattices are given over here with face center and this. Now, let us come to the Miller indices. What are the Miller indices? So, just now I told you that silicon is having a cuboid structure. Likewise, every crystal is having a particular cube type of thing. That cube type of thing, how that is being aligned, in which plane it is being aligned. That will decide the Miller indices. How these Miller indices are decided, which is shown in these 2 diagrams. So first example is shown over here. Whatever the plane is there, this blue color plane, you can extend this to the inside or outside to make it a cuboid, right? You can extend it and then this will become a cuboid. So this plane basically is going to intercept on A and B and C axis at some value. That particular value you have to put over here. That is nothing but the intercepts on the axis. So if you remember, you can recall the plane equation in the form of intercepts. It was x by A, y by B plus z by C is equal to 1. Z by C is equal to 1. This was the equation of the plane, where A, B, C are the intersections, right? So here, if I am taking the reciprocal of these intersections, then I can represent these as the Miller indices, and I will be representing these with H, K, L. So these are the Miller indices. Just take the inverse of these ABC, and these are nothing but the Miller indices. So in this particular example, we can see A is cutting at 1, B is cutting at 1, and it is parallel to C axis, right? So it will never cut to the C axis, right? It is not going to meet the C axis at any point of time. So it means this is 1, 1, and 0. These are the Miller indices. Likewise, we can take another example. So the other example, let's come to the next one. We can see that this plane is parallel to YZ axis. This plane is parallel to YZ axis. It means it is not going to cut the Y and Z axis ever. It is only going to cut the E axis. Right now it is going to cut it 2. So it means 1 by 2 you can take. Sorry, it is going to cut at 1 by 2, let's say. So just inverse of that, you can take 2, 2, 0, 0. That's the plane. That's the plane. So for silicon, most widely used planes are 110, 100, and 111. These are the orientation planes which are commercially used. Most widely commercially used planes are these. Okay. Then there is a set of planes. So these are the Miller indices. Set of planes are actually presented by these brackets. Set of planes. It means similar to those planes and other categories. So these different planes will have a different type of superficial properties, different strain conditions, different mobility materials. A little bit tuning is going to happen. Okay. So based on that, these different type of planes are actually discussed. Now, we are having 7 minutes left. So we'll discuss this in some other lecture. By that time, if you have any questions so far, we can discuss. If you have any questions so far, we can discuss those questions. You may type in the chat box if you have any questions. Yes, do you have any questions? Am I audible? Type Y if I am audible. Not audible. Nitinji, maybe you can restart the Teams again if it is not audible, because there might be some issue of internet or something at your end. No questions. Okay. No questions. So shall we stop for the day, or we can extend it for half an hour if you can permit? Because on Sunday, the schedule is going to be disturbed because of some official assignment given to me. So if you do agree, we can start at 1 o'clock for half an hour, because today half an hour was actually because of some reason it was not done. So if you permit, we can actually go for half an hour or 40 minutes. Yes. Okay. So shall we continue right now? Let's continue right now. And we'll just have half an hour. After that, we will actually stop. Okay. Because the lecture which is going to start at 5 p.m. that actually has whatever I was expected to teach in this particular lecture as a prerequisite. So thank you so much. So let us start the types of semiconductors. So as I told you, there are 2 types of semiconductors based on how it is procured. Means what type of material it is going to have, right? So first one is the elemental semiconductor, and second one is the compound semiconductor. Like silicon is the elemental semiconductor, while gallium arsenide, silicon, germanium, even group 4 elements can also be shared in the equal amount. That is also a kind of semiconductor, right? Gallium arsenide can be there, PBS can be there. Likewise, there are aluminium gallium arsenide. So these type of semiconductors are available, compound semiconductors, which are depending on what type of band gap we want to do, depending on that, how much quantity you have to prepare. For example, aluminium gallium arsenide. So aluminium, gallium, both of these are actually the having the valency 3, right? 3 electrons in the outermost shell, while this is having 5 electrons in the outermost shell. So basically, aluminium and gallium, one part of it will be taken, while arsenic, one part will be taken, so that average 4 can be achieved. So we used to represent it in this way, that 1 minus x fraction part of this, and get this x part of your gallium will be taken. So these are also the type of compound semiconductor materials. Now, based on whether these are doped or not, these are again of 2 types. First one is the intrinsic and extrinsic. Intrinsic means it is the pure form. This is not having any kind of impurity inside it. That is the intrinsic semiconductor. So intrinsic semiconductor, how it is prepared and how it is done. So achieving 100% purity is quite impossible. This 100% purity is quite impossible. And how this impurity affects, let us discuss that also. Basically, this is the energy band diagram for the pure semiconductor, pure silicon semiconductor, let's say, or any semiconductor. So here there is valence band and there is conduction band. Silicon at room temperature is expected to have, every semiconductor, in fact, at room temperature is expected to have some intrinsic charge carriers. So for silicon, the value at room temperature is 1.5 into 10 raised to power 10 atoms per centimeter, carriers per centimeter cube. This is the standard value for room temperature for silicon. If we are changing the material, let's say germanium or something else, then this value is going to change. Okay. So for silicon, it is 1.5 into 10 raised to power 10. These are the elements, electrons and holes available in the silicon structure, even though it is pure silicon structure. Approximately 10 raised to power 22 atoms per centimeter cube are available for silicon. In 1 centimeter cube, approximately 10 raised to power 22 atoms are available in silicon. Right. So this intrinsic number of electrons and holes, intrinsic carriers, Ni, we will be representing this by Ni. N means electrons, N stands for negatively charged particles, I for intrinsic, right? So this is 1.5 into 10 raised to power 10. Now, if you want to modulate it, so you can increase the temperature. If you can increase the temperature, this value is going to go up. If you are going to decrease the temperature, decreasing the temperature, what is going to do is, decreasing the temperature is actually decreasing our energy. Decreasing the energy means the electrons and holes are actually tightly packed. These electrons from the valence band, these were there in the valence band, are not having enough energy to go and sit into the conduction band. Lowering down the temperature to 0 degree Kelvin, what it is going to do is, there is no temperature or energy for thermal energy for the electrons to come to the conduction band. So at 0 degree Kelvin, you can see over here, there is no empty place at the valence band, and hence there is no running electron in the conduction band. What is the hole? First, let us come to the point. What is the hole? Hole is the vacancy of the electron. Let us assume that you have a class. In your class, there are different branches. Let's say one student is sitting here, one student is sitting here, and this space is free. One student is sitting here, one is sitting here, and like this, the sitting arrangement is there. So you can see over here, there are 2 seats which are free. So what any one of others, what they can think, okay, I will go from here to here. Just like that. He thinks that I can go over here. So if this particular person is moving from here to here, it means this particular seat is getting vacant. This seat is filled now, and this becomes vacant. So this vacancy is nothing but hole. And whatever the person is moving from that particular place to another place, that was the electron. Once this particular person and this particular seat, which is fixed, then that becomes the complete structure. Then there is no failure. Electrons and holes which are combining together, there is no structure left. We call this as recombination. And temperature is going to increase. It means there is a generation of electron and hole field. Okay. For example, let's say some good thing is happening outside of the class. So person is going outside, and this person going outside means this particular seat is vacant, and this particular seat vacant means this is a hole created. That's how these holes are being created, because electrons will jump and go over here because they are having the kinetic energy or some other type of energy. So it is for intrinsic type of semiconductors, right? And at 0 degree temperature, there is no electron or hole available, because all electrons are occupying their wanted space. So they are not free to move from the conduction band to the valence band to the conduction band. When they actually were moving from valence band to the conduction band in intrinsic semiconductor, they were leaving behind the empty space that is equivalent to the empty chairs. So these actually is known as hole. So the number of holes is equal to the number of electrons. We will represent this by Ni. So it means the Ni is same for holes and electrons. Intrinsic carrier concentration is same for electrons and holes. Okay. Another one is the extrinsic semiconductor. Extrinsic semiconductors are also known as impure semiconductor or doped semiconductor. The semiconductors which are pure, those are having very less conductivity. In order to make them conductive conductors category, we have to make some doping, some external elements we have to dope in. So there are two types of doping, trivalent and pentavalent. So trivalent, like group 13 elements like aluminium, gallium, boron, you can take. Right? These are having 3 electrons in the outermost shell. So if we are having trivalent impurity, it means there is vacancy of 1 electron, right? So that vacancy of 1 electron is there. That electron, if these are taken from somewhere, so it means these are negatively charged ions. These will be negatively charged ions. Okay. Otherwise, these are having a hole. Hole means vacancy of electron, means these are ready to occupy 1 electron, right? If you are having pentavalent impurity, like phosphorus is there, antimony is there. So in these, 5 electrons are there in the outermost shell. So 4 electrons are used to make the covalent bonds. 4 electrons are used to make the covalent bonds. So 1 electron in N-type semiconductor is free to move. That particular free electron is having higher energy as compared to others. That is going to go into the conduction band. That is going to go into the conduction band, right? So once it is going to reach to the conduction band, it means the mobility is going to increase. The more number of carriers are available, mobile charge carriers are available to move freely across conduction band. So that is contributing to the current flow, right? So this particular band diagram is shown for the N-type semiconductors. It is seen that the Fermi level has been shifted towards the conduction band. The Fermi level of this has been shifted towards the conduction band, and there is one donor energy level that is actually just above the Fermi level, and there are ample number of electrons available, right? So this is how it is going to work. Another one is P-type semiconductors. In P-type semiconductors like boron, aluminium, gallium, etc., the EF is going to go to the valence band side because we are having much more holes available with us. Aluminium means there is vacancy of electron. Vacancy of electron we are denoting by hole. So it means more holes are there. More holes are available. It means these holes are available in the valence band. Right? These holes are available in the valence band. Now, along with these, what other things are going to happen? Along with this, what other things are going to happen? So let us discuss. If you have a trivalent impurity or pentavalent impurity along with these charge carriers, another thing is going to happen. Let's say this is aluminium. So this is aluminium and I am having silicon which are side by to this. So two electrons, and one electron now is left for aluminium. So it need one more electron. It need one more electron to get into the stable condition. But this electron is not available, right? But this electron is not available, so this creates a hole. This is going to create a hole. Here there is a hole. This hole is available. Now, this electron which was belonging to aluminium, it sees that, okay, there is a hole. Or maybe there are Ni electrons flowing into the structure. These Ni electrons, intrinsic electrons, those are available, right? 10 raised to power 10, I told you, the order of those electrons freely available are 10 raised to power 10. So some electrons are available and some holes are also available in the space, material space. So those electrons will see, okay, this is also the place to sit. So this is going to sit over here. If it is going to sit over here, it means this hole is occupied. If this hole is occupied now, so what type of charge aluminium will have? Yes, please tell me, positive or negative? The charge on aluminium, we will have positively charged or negatively charged ion. Yes, any comment? So aluminium will become negatively charged because it is having one extra electron which is sitting over here. So that's what it is, negatively charged ion. Remember, there are two things. One is the ion, another one is the free mobile carriers. So ions are these. This aluminium is the ion. It is actually much more heavier than the electrons and holes, and electrons and holes are much more light. If those are lighter, they can actually move here and there, and those are contributing to the current. But these ions are not moving. We are not able to move these ions. So these are not contributing to the current, but yes, these ions are available in the space. In that material space, the ions are available, right? So likewise, if we talk about the other material, instead of aluminium, if I'm going to take, let's say, phosphorus. So the phosphorus was having one more extra electron. So two electrons will come like this, and one more extra electron will be available. So other surroundings are silicon, and electrons and holes are there in the material space. So this extra electron, which was belonging to the p type, right? So sorry, hole is not flowing in the free space, only electrons are flowing in the free space. Holes are available over here. Hole is the vacancy, right? So it is available at the place where the electron can sit. So this electron sees, okay, if hole is available and it can sit over here. If it is going to sit over here, it means one electron is actually vanishing. And along with that, one hole is also combining. So this is known as the electron hole recombination, right? This electron came out of this p material. P is the phosphorus. This is coming out of this. So what is the charge on P? Phosphorus. What will be the charge on phosphorus? For n-type material, what is the charge on phosphorus? These are positively charged ions. These are positively charged ions. Ions will be denoted by this and this. And free mobile carriers will be denoted, electrons will be denoted by this, and holes will be denoted by the empty space, as shown, right? So ions are denoted by the fixed ions. So we will enclose them into a circle, plus and minus. Plus represents positive ions, minus represents negative ions. Dot represents, this dot represents electron, free electron. This represents the hole. So the hole will be there in the structure. Electron is free to move into the structure, right? Any questions so far? Yes, any question? So we have gone through the electrons and holes, right? So now let's come to the next. What is the silicon behavior? So silicon will behave at times like insulator. When it can behave like insulator. So in order to make the behavior like insulator, we have to make sure that it is not doped, or and along with that it is at 0 degree Kelvin. Doping is not there and 0 degree Kelvin, 0 degree Kelvin, 0 Kelvin or 0 degree Kelvin. It is not okay, it is 0 degree Kelvin. It can behave like semiconductor at room temperature if it is pure. So it will behave like semiconductor at room temperature, even though it is pure. If we are doping it a little bit, then the conductivity increases. So increasing the conductivity means you are doping it Na type or Nd type. And A means acceptor type. Acceptor means it is going to accept the electrons. And D stands for donor type. So if it is donating the electrons, so what type of charge will be there on this? What type of ions will be there? So these will be donating electrons, means one electron is donated. So one electron is donated means electron is out from this. So this is positively charged. Donating the electron. First, positive and negative were altogether same. So now the one electron is less. Let's say for first force there were 15 electrons and 15 holes. 15 protons. So one electron means one electron is gone away. So it means one proton is extra. So this is positively charged ion. And likewise, this is negatively charged. Acceptors, it is going to accept one electron. So it is negatively charged ion. Because it has taken one electron, so it is having negative charge on it. Protons are lesser than the electrons, right? Yes. So there is the charge neutrality equation. Charge neutrality equation. What it says? Charge neutrality equation says that the number of fixed ions plus the number of mobile charge carriers. If a semiconductor is not having any external applied field, let's say there is a semiconductor bar. There is a semiconductor bar. It is not having any externally applied field, right? No externally applied field is there. So the number of free charge carriers, if it is N type, right? So N plus Nd. There will be donor type impurities, right? N plus Nd. This N is actually negatively charged, Nd is positively fixed ions. So one type of positive and negative balancing is expected to be there. So these actually come to the equilibrium condition. So Nd will go to the opposite side, right? Nd plus. This is positive type, N is negative type. What else was there? There is one controlling equation which says that total number of electrons into holes is equal to Ni square. So if it is N type, then P, the holes will be minority. So this is in majority, N is in majority, number of electrons will be equal to the doping concentration Nd plus. If we will use this, we'll get that the minority carriers will denoted by Pn. That is Ni square, intrinsic semiconductor carrier concentration, square of that divided by Nd. So this will be the carrier minority carrier concentration for N-type semiconductor. Likewise, if I have a semiconductor bar which is of P-type, so in P-type, I have acceptor ions. Acceptor ions means P is the number of holes, which is holes are expected to be positive type. And Na are the acceptor ions. Acceptor ions were one electron they are taking. Taking the electrons, protons were, let's say, aluminum. Protons were 13, one electron is taken. So electrons are 14. So it means, can I say that this is negatively charged? This is negatively charged. Holes were positive. So majority charge carriers P, I can represent P is equal to Na. So I will apply the same formula, Np is equal to Ni square, mass action law. So what I will get? Np. This P means in P type of semiconductor structure. N type, N means the electrons in P type of semiconductor. What it will be its value? Ni square divided by Na. So these are the formulas which we should remember, and this is known as the mass action law. And these Na and Nd are the doping concentrations of acceptors. Na is for acceptors and Nd is for donors. Donors are positively charged ions, while acceptors are the negatively charged ions. So I'm so sorry. I got some urgent calls. So basically, Na is negatively charged ion, Nd is the positively charged ion, N and P, these are the mobile charge carriers. N stands for negative, P stands for positive. Negative means there are electrons. Electrons, we say that electrons are having negative charge on it. So we call N means it is negative, P means it is positive, right? So you're closed. Slideshow, you're closed.
Maybe I'm not closed. Maybe share it again. You joined by your mobile.
Am I audible now? There was some internet issue, so because of that, we got some disturbance. Thank you so much. So I will take another 4 or 5 minutes, and then we will close for the day. For this particular session, we'll close. Yeah. So basically, there are two types of materials: N-type and P-type. In N-type, we'll be having N. N for negative. N is the electron, right? So N for negative. N means negative. So mobile charge carrier is negative. Okay.
Yes, can stop.
Connection
Yes.
goes to.
Okay.
Yeah. So N means it is negative and P means it is positive. So if N type is there, then whatever we need to work on is mainly electrons. These are the negatively charged electrons. And for P type, we are focusing on holes. Holes are nothing but the vacancy of the electrons. The value of these will be equal to Nd. Nd are the ions, doping concentration of that particular type of material, pentavalent impurity. P is equal to Na, holes. This is equal to the acceptor impurities, equal to the acceptor impurities, right? So what are the different applications? In the solid state devices, we'll find applications in the diodes, transistors, and these are finding the applications in MEMS sensors, devices like diodes, MOSFETs, their applications to circuits and systems. So these we will be covering into details in this particular subject. If you have any query, you please feel free to ask. We have 9 more minutes. If you have any query, please feel free to ask so that we can complete this session. Am I audible? Yeah, screen was not visible earlier because of some internet issue. I hope now it is visible. We have completed it. Yes, am I audible? Anybody is having questions? No questions? If there are no questions, then shall we stop for the day? So the attendance is recorded, right? Yes. Okay. So we have recorded your attendance for this session. So we'll be counting this as like starting from 11 to 1:30, we'll be counting. On Sunday, there is a mismatch because of some official duty. So I will inform you that which lecture can be actually taken later for Sunday. So probably there is lecture 12 to 1 that I need to reschedule maybe. And evening maybe 5 to 6 we have to reschedule. We will start at 6 and we will end up maybe 7:30 or somewhat like that. So we need your support in that because of some unavoidable duty. I cannot actually make it that on time. So is there any question or shall we stop for this session? Please speak, speaker. उनका mic mute कर दो.
No, actually you cannot. Chat ही कर सकते हैं.
So you can actually chat it. Yeah, Dr. Sakshi Ahuja. No questions for now. No problem. We'll be there for next 10 days. So if you have any questions, you can ask in other session also. Questions related to me or some other speaker, you can post in other session also. There is Canvas invitation shared to all of you. You feel free to put up your questions over there also. You have that facility over there, right? So you please join that. That was invitation was given with a separate link. So please type Canvas in your this email ID search engine, and it is going to give you the details. So please join that so that the study material, PPTs and related things, the video links and all these things we will be sharing through that. Okay, so shall we stop for this session? Speak up at least something you can speak or maybe type. Okay then, thank you so much and have a nice learning. Thank you. Let us meet at 5 p.m. again at the evening time. So we are extremely sorry you have faced some problems due to some issues from our side. But now it should go smoothly. I believe there must be no issue in the Teams link joining in upcoming sessions. So thank you so much.
This is for Canvas.
Yeah, for Canvas, you might have got something from this particular email ID, notifications@infrastructure.com. So please check the invitation came from here and accept that. Okay, then you will be able to join that particular course. It is there in your link. If it is still not there, you feel free to tell me in the evening session. I will be there, and we will send some of the candidates who have joined maybe today or yesterday. They can actually inform. So those who are interested, means if some of your colleagues or somebody is interested, we have opened the joining link till tomorrow evening as well. So those who are interested may join. Thank you so much. Have a nice day. Thank you.
Stop the recording.
Um,